Now we will look at a very, very interesting binary star system, the Algol system. It was actually known as the demon star. So, this star system had been a mystery. Let's see, why is a star mystery and how do we resolve the mystery? Okay. This is a binary star system. You look at the classification. One is a B8 type classification. The other is K2 type classification. Okay. So, from HR diagram, you should have an idea what is the nature of a B8 star, what is the nature of a K2 star. You also know what the intrinsic luminosities of a B8 type of star and the K2 type of star is like. Okay. And then you have an estimate, if they are moving around each other, what should the eclipsing light curve look like? Now look here. When you have the primary dip occurring, it is a massive dip occurring, and the second and the third contacts are very close to each other. So they are very similar in their sizes, right? In fact, sometimes it might occur here that the third contact is happening before the second contact. That is also possible. It's nearly something like that happening out here. Okay. Then what happens is that for the secondary eclipse, you get this kind of a shape and the amount of light that is blocked is so low. This expectation doesn't fit the idea of the stars that we have from our HR diagram, right? We do not expect this kind of an obscuration happening where, the second contact is happening after the third contact, and hence you get something like this, and the amount of light that is blocked that you get from here, the relative amount of light that you got blocked here and here, they do not fit your picture of the standard stellar model. So the question is, what is happening? Let's have a look at it and try to explain what is happening. So, imagine this system when it was formed. Star 1 was the more massive of the two stars. It was a blue type star. And most likely, from the models that has been created, the mass was 3 times of the second star. So, the second star was a red star. It was a cooler star. Red means cool, right? Blue means hot. It is just the opposite of the artistic point of view. Okay, in physics, thermodynamics, when we talk about red color and the blue color, blue is always hotter than red. In art, we always assume blue to be associated with water and red associated with fire. So in art, red is always hotter than blue. But in physics, blue is always hotter than red. Okay. So we have a blue star, 3 times the mass, and hence this has a much more luminosity, should have much more luminosity. Now understand something very, very carefully. This is the equipotential diagram. Okay. What we mean is that these lines are the circular lines, are the lines of equal potential. Here these lines correspond to the potential of this object. Here these lines correspond to this object. But of course, it is always a sum of these two, right? Very near to this object, the potential lines are less influenced by this object, and very near to this object, the potential lines are less influenced by this object. Okay. At every other place, it is the sum of the two, right? And if you go to very far away, then it will behave like a circular where the potential is due to the sum of these two, right? And these lines which are normal to the circular surfaces, these are the gradients, okay? These are the lines of the gravitational field. This is the line along which a particle will move, okay, if it is set free. Now, look at this point. This is the point where the circle due to this object and the circle due to this object, not exactly the circle, it is deformed because here it is experiencing both. And this is the point where the gravitational potential due to this and this is equal. So, this is a point of equilibrium. At exactly that point, there is no force acting. But if you displace slightly in this direction, it will fall in this direction. If you displace slightly in this direction, it will fall in this direction. This is known as the, technically known as the inner Lagrangian point. Now, when this happens, that suppose a particular star is located here, if it happens to fill this region by expanding during its evolution, then what will happen? The surface of the star touches the inner Lagrangian point. And this region is actually known as the Roche lobe, named after the astronomer Roche, who first gave a detailed picture of this forces acting. So now what happens, that when this particular star fills up its Roche lobe, then it becomes a semi-contact binary. Now, any mass at this surface will be very easily transferred on this. Okay? A little bit of push due to some action of pressure and temperature will push the mass here. And if it tries to expand more in the process of its own evolution, then the mass will travel and be transferred to this particular star. So, what we see is now this picture. This was a picture that we saw. We start off with a hot blue star and a cooler reddish star. Okay. When we say blue and red, it is always actually relative. What we mean is hotter and cooler. Okay. Then this particular star filled its Roche lobe. It expanded. Why did it expand? Because this is a blue star. This will evolve faster, much faster than this star. And hence it will expand. And once it fills the Roche lobe, now the mass will start flowing into this companion star through the inner Lagrangian point. Okay? So, if you read what is written out here, star is ascended to the giant branch, it overflowed its Roche lobe and gas began to flow onto star 2, reducing the mass of star 1. Understand, it is losing mass. And what happens when you lose mass? Now this mass is more, this mass is less, right? So the whole equipotential structure changes. Okay, this Roche lobe, the inner Lagrangian point will shift. Okay, so this causes a very, very complex interaction between the two stars, where you have an episode where one star is losing mass, the other star is gaining mass artificially, right? When I say artificially, this affects the whole evolution process had it been a unary star, a single star. So now the whole evolution of the star changes. And that is why when we look at the evolution of stars, we should be very much aware that when it comes to a binary system, especially a semi-detached binary or a close contact binary, then the evolution process can change and they will influence each other's evolution. Okay? So, now what happens is this star, which was actually a cooler star, gains mass. So you see the transition happening from red to yellow to blue. So now this star has gained mass. What happens when you gain mass? You go back to your stellar physics. More mass, more gravity, more temperature, more nuclear reaction, more temperature, and your color will change to blue. Your spectral type now changes. You had started as a certain spectral type which was cold. Now you have become a spectral type that is hot. And here you have lost the mass, right? So your spectral type anyway will change because it is evolving, going through the giant phase. But this evolution is further complicated by the fact that now you have become a smaller star, but still, and you have become a smaller star and cooler star because you have lost mass. Okay, so that is what is changing the whole evolution of this binary star system. And that is how the whole explanation of the light curve of the eclipsing binary of Algol is explained. That the mass transfer between the stars during its course of evolution has changed its spectral classification. Okay, so this is an excellent example of how your mass transfer can happen in a semi-detached binary system. And that completely changes the nature of the evolutionary path that every individual star takes. And hence, the light curve of the eclipsed binary system is not as expected as you would expect from typical spectral classifications of the stars.